Okay, same paper. The next question is, so this is the paper, February, March 2022, and paper 4.2. I have already solved for you just to save the time. So the question is, polonium 211 decays by alpha emission to form a stable isotope of the lead. Complete the equation for this decay. I mean, each polonium is emitting one alpha particle and it is converted into lead. Look, when alpha is emitted, 2 protons and 2 neutrons are released from the nucleus. So it means alpha is carrying 2 protons and 2 plus 2, 4 nucleons. So this is a symbol for the alpha. So when 2 number decreases from 84, this becomes 82, and this mass number decreases by 4, so it becomes 207. So this is the answer for this. The variation with time t of the number of the unstable nuclei and in the symbol of the polonium is shown in the figure, okay? So initially the number is 24 in 10 power 12, and then gradually it is decreasing after emitting alpha particles. So each polonium is emitting 1 alpha particle. It is visible from this equation. Now the question is at time t0, the sample contains only polonium, okay? Use the figure 9.1 to determine the decay constant lambda. So give a unit for your answer. So from the graph, we can determine the half-life. So initially number is 24, and after half-life it becomes 12, and the time for these 12 is given here. So this is the half-life, it is approximately 0.52. So the half-life is 0.52 seconds, and the lambda decay constant is ln 1/2 or 0.693 divided by half-life. So 0.693 divided by 0.52. The answer is coming 1.3. The time is in second, so the lambda will be in second power minus 1. Next is use the answer to calculate the activity of the sample at T0. For the polonium, activity A is equal to lambda. Lambda is calculated 1.3, and at time 0, what is the number of the polonium at time 0? The number of the polonium is 12 times 10 power 12. Sorry, number is 24, not 12, 24 into 10 power 12. So here, 24 10 power 12, after calculation, you will get this answer, and activity is measured in backward. If one nucleus decay in 1 second, then the activity is 1 backward. So here the 1 backward. Sketch the line to show the variation with time t of the number of the lead nuclei in the sample. So the polonium is converted into the lead, okay? So look at the graph. After 1 half-life, half of the polonium, mean 12 out of 24 converted into the lead. So initially there is no lead. So that at time 0, the number of the lead nuclei is 0, and after half-life it becomes half, mean 12, and after second half-life, this one, so this 12 becomes 6, mean 6 more number of the lead. So we will add 6 more in the 12, so it becomes 18. So after second half-life, the number of the lead becomes 18. Look, initially polonium is 24 and the lead is 0. After half-life, this becomes 12. It means 12 decays, and decays converted into the polonium after first half-life. And the second half-life, it becomes 6. So 12 minus 6, these 6 are converted into the lead. So 12 plus 6, it becomes 18. And then it becomes 3, so it becomes 21. So look, this polonium is decaying and this lead is increasing. So it means the polonium is converted into the lead. So this is the graph. So you have to join these 3 points. At 0, lead is 0. After half-life, it becomes 12. After second half-life, it becomes 18, and so on. And after fourth half-life, it becomes 21. So this is the graph, And the next is calculate in joule the total amount of energy given by the alpha particle that are emitted between time 0.3 and 0.94. So each decay releases the alpha particle with energy. This is the energy of the one alpha. So first we have to calculate how many alpha are emitted. So each nucleus emitting one alpha particle. So we will calculate actually the number of the nuclei decays in this time. So look at time 0.3 second. At the time 0.3, we can check the number of the nuclei. And the number of the nuclei are 16 into 10 power 12. And after time 0.9, the number is this, remaining number. So what is the number of decay? Delta n. The difference of these two, 16 minus 7.2, 10 power 12. So it is approximately 8.8 10 power 12. So 8.8 10 power 12 polonium nuclei are decaying. Mean these are the numbers of the alpha also, because each nucleus emitting one alpha. So one alpha particle is carrying this energy. So this energy, 6,900 kilo electron volt, so kilo 10 power 3, and 1 electron volt is 1.6 in 10 power minus 19. This is the energy in joule for the one alpha, but we have this number of the alpha. After multiplication, we will calculate this 9.7 joule. I repeat this. First, each polonium nucleus after decay emitting one alpha. So how many nuclei were decayed during this time? So at 0.3, this is the number of undecayed, and after 0.9, this is the number of the undecayed left. What is the number of decays? The difference of these two. So this is the number of the nuclei decayed. So it means number of the alpha particle. Now one alpha particle carrying energy 69,000 kilo electron volt. This is for the kilo, this is for electron volt, and this is the energy for 1 in joule. Multiply by number of the alpha particle, you will get this answer. Next, suggest why the total amount of the energy released by decay process between time this 0.3 to 0.9 is greater than, yes, because some of the energy is also carried by the lead nucleus as a kinetic energy. So this is the atom. After emission of alpha particle, law of conservation of the momentum. Total momentum before collision is equal to total momentum after collision. Initially, the momentum is 0. But when alpha is emitted with some energy, so definitely the remaining nucleus will move in the opposite direction. So it means some of the energy is also carried by the lead. That's why the answer is not accurate. Some of the energy is carried by the lead nucleus as a kinetic energy, because after the emission of the alpha particle, the remaining nucleus, the daughter nucleus, will recoil in the opposite direction to get the zero momentum. Next question. In an X-ray tube, electron accelerated through a potential difference of 75 kilovolt, 75,000. The electrons then strike a tungsten target of efficiency, effective mass, 15 gram. The electron energy is converted into the energy of the X-ray photon with an efficiency of just 5%. The rest of the energy is converted into thermal energy. The X-ray tube produces an image using a current of 0.40 ampere for a time of 20 milliseconds. The specific heat capacity of the tungsten is 130 joule per kg per Kelvin. Determine the temperature. Look, E is equal to mc delta theta. E is the heat energy. Energy is power multiplied by time. And the power is current into voltage. So energy is IVT. So IVT is equal to mc delta theta. Current given 0.4, voltage given 75,000, and the time 20 millisecond. The mass in kg is 15 in 10 power minus 3. The specific capacity is 130. But look at this 5%. So it means the 95% mass is effective here. So we have to multiply this with the 0.95 as well. So because the target of the effective mass is 15 gram, the electron energy is converted to the energy of the X-ray photon with the efficiency of 5%. So the X-ray is carrying 5%, and the remaining 95% is converted as a heat energy. So here we are using energy for the heat. So that's why we have to use here the 95%, because the 95% energy is converted into heat energy. That's why we have to take the 95% of MC delta theta. So 95% mean 0.95 specific capacity change of temperature, and after calculation we will get this temperature change, which is 290. So do remember, 5% energy is carried as photon and the 95% is converted into the heat energy. That's why we are using here 95% of MC delta theta. Next, the linear attenuation coefficient of the X-ray photon is the muscle is 0.22 centimeter per centimeter. Calculate the thickness of the muscle that will absorb 80% of the incident. So if 80% is absorbed, then the 20% is transmitted intensity. So I over I naught E minus Bx. So here, this is not the absorbed intensity, this is the transmitted. So instead of the 80%, we have to write here the 20% because 80% is absorbed. So I over I naught is 20%, and the 20% mean 20 divided by 100, it becomes 0.2. So this fraction becomes 0.2. And E power mu is given 0.22 into X, taking ln log both sides. So ln 0.20 minus 1.61, and then minus cancelled, so X is 7.3 approximately. So do remember, you have to use here 20% because the transmitted intensity is 20%. 80% is absorbed. So this is the question, this is the part B. Move to the next. Table 10.1 shows the linear attenuation coefficient mu for the X-ray photon in the different tissues, bone, blood, and the muscle. Two X-ray images taken, one of the equation, one of equal thicknesses of the bone and the muscle, another of the equal thickness of the blood and the muscle. So bone and muscle and blood and muscle. Explain why one of these images have good contrast but other does not. Look, there is a huge difference between linear attenuation coefficient between bone and the muscle. Bone and the muscle, 3 and 0.22, huge difference. So due to the different amount of the X-ray absorption, due to different linear absorption coefficient, different amount of the X-ray is absorbed. So due to different amount of the absorption, they will give you the good contrast. So definitely there will be better contrast between bone and the muscle instead of the blood and muscle, because the blood and muscle linear absorption coefficient almost same, 0.22 and 0.23. So this is the question. Next, positron emission tomography scanning obtain diagnostic information from a person. The information is used to form an image. PET scanning uses a tracer. Explain what is meant by tracer. Substance containing radioactive nuclei that is introduced or injected into the patient body for the tissue study or to study the rate of metabolic activity. You can write rate of metabolism, rate of metabolic activity is called tracer. Instead of tissue study, you can also write, it's better to write rate of metabolic process. Next, PET scanning involving inhalation. Explain what is meant by inhalation. When particle interacts with its anti-particle, mass of the both is converted into energy. This is called annihilation. Mean, for example, electron and positron. When electron and positron will interact with each other, the mass of the proton and the mass of the positron and mass of the electron both converted into energy. That's why when we have to calculate the energy, we will write mass of the electron, mass of the proton into c square. This is annihilation. Calculate the total amount energy released. Inhalation, so look at this, energy of the annihilation, mass of the electron plus mass of the positron into c square. So both are anti-particles, so they have the same mass. So 2 mc square, 2 mass of the electron is 9.11, 10 power minus 31. You can check from the data sheet. and into speed of light 3 into 10 power 8 square. The answer is this. And the next, calculate the wavelength of the each gamma released. This is the energy which is carried by each photon. Mean this is energy of both photons. So that's why the energy of the electron plus energy of the positron is equal to the total energy, which is calculated. So 2hc over lambda. So the lambda is equal to 2hc over E. This 2 is coming because the energy is calculated from the both masses. That's why we are multiplying hc over lambda by 2, because this is the energy of both. So lambda is equal to 2, and the Planck constant 6.63 10 power minus 34, speed of light, and then energy which is calculated here. So you will get the wavelength of each 2.4 into 10 power 12 meter. Next, explain how the gamma photons are used to produce an image. 2 gamma ray photons are emitted during inhalation process. Both travel in the opposite direction, carrying same momentum, but the total momentum remains same, remains 0. They are detected by the detector. X-ray photons arrive at the detector at different times. It helps in the detection of the location of the production of the X-ray photons, mean the point where there is a radioactive material which is emitting the gamma ray photons. So we can locate the radioactive tracer. They are processed, mean the gamma ray photons, they are processed to convert into the visible light photons and imaging of the tracer concentration in the tissue. And after imaging, we can check the concentration of the tracer concentrated in the tissue. Mean we can check the position, we can check the metabolic activity, mean the concentration of the tracer in the tissue. Next, state what is meant by luminosity. Total power radiant at the surface of the star is called the luminosity. The luminosity of the sun is given 3.83 10 power 26. The distance between the earth and the sun is 1.51 10 power 11. Calculate the radiant flux intensity F of the sun at the earth. Give a unit with your answer. So F, radiant flux intensity, is L divided by 4 pi d square. So L is equal to 3.83 into 10 power 26. 4 into pi value, either 22 by 7 or 3.14. And the distance is given here 1.5 into 10 power minus 11, and then square. So you will get answer 1340. And this is flux intensity, mean watts per meter square. Use the data to calculate the mass that is converted into energy every second in the sun. Energy is equal to mc square. And m is equal to energy divided by c square. So energy is power divided by time. So radiant power is given 3.83 10 power 26 they're given. And every second, so look, time, and it means the power is equal to energy due to time 1 second. So energy is equal to 3.83 10 power 26 in 1 second divided by speed of light square 3 to 10 power 8 square. The answer is coming this. So 4.26 and 10 power 9 mass is converted into energy. Next, the radius of the sun is 6.96 10 power 8. Show that the temperature is 5770 Kelvin. Look, L, luminosity, is equal to 4 pi sigma r square t power 4. Luminosity is given 4 pi, and the Stephen Boltzmann constant from the data sheet 5.67 10 power minus 8. And the radius is given 6.96 10 power 8, it's square, and the temperature power 4. So temperature is required. So T is equal to this value multiplied by 7 divided by this, and whole power 1 by 4, because we have to calculate this T. So after calculation, the answer is coming 5,770 Kelvin. So Stephen Boltzmann constant, sigma, and by using this law. Next, the wavelength lambda max of the light for which the maximum rate of emission occurs from the sun is 5 into 10 power minus 7 meter. Look, 3 significant figure, 5.00. So the temperature of the surface of the star is 9940 K. Use information to determine the wavelength of the light from which the maximum rate of the emission occurs. Look, lambda max is inversely proportional to temperature. Mean lambda 1 over lambda 2 is equal to T2 over T1. So the lambda 1, this is given here, and divided by second lambda is required. So the temperature related to this is 9940, and the temperature calculated here. So we have to calculate the wavelength related to this one. So the lambda, this is 577, and after multiplication, cross multiplication, the lambda is coming 2.90 10 power minus 7. We have to write this in 3 significant figure. So this is the paper. Okay, good luck.